In this presentation, we introduce ScaTE, a scalable framework for self-supervised traversability estimation for navigation in unstructured environments. Estimating the traversability of a driving surface is an essential component of autonomous driving systems. However, most of these methods rely on human-annotated large-scale datasets to learn the traversability of terrain. This can be labor-intensive and error-prone. For safe and reliable navigation in unstructured off-road environments with a variety of challenging terrain, the estimated traversability should vary based on the driving capability of each vehicle. To learn the terrain's vehicle-specific traversability, recent research has focused on self-supervised learning methods that leverage a vehicle's driving experience. The self-supervised approaches use actual driving experiences rather than human-provided annotations, resulting in varied results for different vehicles. Various self-supervised learning methods have shown promising performance for navigation. However, these methods are tailored for specific types of vehicles and therefore, the learning methodologies are not scalable. It also has an inherent uncertainty problem. This is because self-supervised data only provides supervision for actually traversed regions. Therefore, such regions should be identified explicitly as non-traversable so that they can be avoided during navigation. In this work, we propose a scalable framework for learning self-supervised traversability that can be self-trained without any external human annotation. Our method learns to regress the traversability that a vehicle would undergo while traversing the terrain. Moreover, our framework uses a positive unlabeled learning method that does not require any human supervision to classify uncertain regions. Our method takes LiDAR point clouds as input. The vehicle-train interaction is measured using proprioceptive sensors, and the collected sensor signals are automatically mapped to the points of contact in the point cloud. These points are considered traversable and labeled as positive, while the remaining points are left unlabeled. For traversability regression, the point features of positive points extracted from the backbone are concatenated with the vehicle state and forwarded to MFPs to regress the traversability. For binary classification for uncertainty handling, the concept of one-class classification is used. Then, the classification feature embedding space is trained to minimize the volume of hypersphere that encloses all of the positive data. In addition to using positive data, we also utilize unlabeled points to obtain more discriminative features and prevent hypersphere collapse. The unlabeled data are clustered with a set of learnable prototype or cluster centers. First, the posterior distribution of the unlabeled points to prototypes is calculated. Second, each point is assigned to one of the prototypes with an equipartition constraint. Cluster assignment can be solved efficiently by a few iterations of the Synchron-Knob algorithm. The feature and prototypes are jointly updated to minimize the cross-entropy loss between the posterior distribution of points and the cluster assignment. We designed an experiment to demonstrate the scalability of our framework using a high-fidelity simulator carmaker. We created an off-road scene with various types of unstructured terrain to collect training data for the 3 types of vehicles and use the vertical forces exerted on each wheel as ground truth traversability. Using this data, distinct traversability models for each vehicle are trained. A sampling-based model predictive controller is used for navigation. We formulate a simple cost function which consists of 2 components. First, the uncertainty cost imposes a significant penalty if the wheel-terrain contact point is non-traversable. Then, the stabilizing cost is an example of a cost function that makes use of the predictive traversability. We conducted navigation experiments on an off-road scene to evaluate our framework. Our framework enables vehicles with different driving capability to learn distinct traversability and navigate along different paths based on the estimated traversabilities. Also, navigating without binary classification or traversability regression resulted in failure. We also demonstrate the efficacy of our framework using real-world driving data with our mobility platform in unstructured environments and a public off-road driving dataset released 3D. We also quantitatively evaluate the quality of our binary classification method. Our method shows a significant margin compared to other one-class classification methods for both datasets. We additionally conducted real-world driving experiments in an off-road environment with another type of our vehicles. The results show that our framework can precisely identify traversal regions and traversability of terrains without any human annotations. Thank you for your time and attention.